Okay, so let's begin with lecture number 2, continuing from the previous lecture of the course Intermediate Nuclear Engineering, which covers diffusion, transport of radiation, as well as Monte Carlo simulation. In the last lecture, I started looking at nuclear radiation and spoke a little bit about flux, and I'll continue this in lecture number 2 today. My name and email addresses, personal and official, are given over here. My cell number is given, and my personal website is www.nucleareng.com. I'll be happy to take any questions or suggestions for the improvement of these lectures. Okay, so let's continue. I was talking about flux and how flux converts into dose. So these two figures, figure 1.2 and 1.3, show the dose factors for neutrons and photons in units of sievert centimeter square. On the x-axis, you see energy in MeV. On the y-axis, you see dose factors for neutrons, dose factors for photons. Now, the important features to understand from these two figures is that for low fluxes, for low energies, there's a lower dose conversion factor, 10 to the minus 11 approximately in this range. And it goes up 2 orders of magnitude at energies in excess of 1 MeV of the projectile neutron. Similarly, over here for photons, you can see that low energy photons are less important than high energy photons in terms of the radiation dose. Now let's come to an important concept of the adjoint flux. Now, as previously I said that the flux phi is a function of 7 variables, 3 space, 1 energy, so 4 plus 2 angle 6 and 1 time. Now, when you talk about the adjoint flux, then it has mathematical as well as physical significance. Mathematically, it is the adjoint. So if it's a matrix, you take the matrix, the adjoint of the matrix, and you obtain the backward transport equation. If you're dealing with the forward transport equation, you can convert it into the backward transport equation. So the adjoint flux is written with a plus superscript over here, so phi plus. Now, when I think of the adjoint flux, I think of my late supervisor, Dr. Jeffrey Lewins, who called this the importance function. And he's got a book on it as well. Essentially, what it says is that you want to go from source to detector or detector to source, a cause-effect relationship. So a forward relationship, for example, if you know the source of energy coming out of the sun, you want to calculate how much radiation is falling on Earth at some location. So that is called a forward problem. A backward problem is where you're given the response of the sun on the Earth and you do not know the source term of the sun. So you want to go backwards from the effect, you want to find the cause. So that is called a backward problem. So this is where adjoint functions are important. So that's why we have the adjoint flux. Now, if you are thinking in terms of variational formulations, then the adjoint flux is also the Lagrange multiplier. So the Lagrange multiplier, as you know, is the sensitivity function, the change in your performance index, in your cost function, divided by the change in your constraint. So that is what we call the adjoint function. That is what it physically represents for the optimal solution, of course. So we'll see more of this when we come to the chapter on variational methods. Another quantity is the neutron current. Now, neutron current J as a vector has the same units as that of neutron flux. It represents the same thing, the rate of flow of neutrons across a unit surface, but the difference is that it is in a direction of unit normal vector to the surface it's crossing, and that's how it's defined as a vector. So if you want to find the boundary crossings, let's call it capital gamma, the leakage from a surface, you dot it with the unit normal vector to the surface it's crossing, integrate over the surface area, and you can convert that through the divergence theorem into div of J integrated now over volume rather than area. So the cause-effect relationship between flux and current, for that we have Fourier's law and Fick's law. Fourier and Fick both said that there is a cause-effect relationship. If there is a grad phi, where phi is a scalar, then there's got to be an effect called J, and J is proportional to the negative of the grad phi. Negative because things can flow from higher to lower, not from lower to higher. And the constant of proportionality is called the diffusion coefficient. So if you define forward and backward angles, so if you look at, if you say that something going between 0 and 90 degrees, scattering forward is going towards the right, and between 90 and 180 degrees is going towards the left, so it's going backwards, so J minus. So then you can say the net current is J plus minus J minus in the forward direction. Okay, now let's come to nuclear data. Now nuclear data and is such an important thing. It's actually pivotal over here, that everything depends on nuclear data, nuclear interaction data. And all the reaction rates in nuclear engineering come from the interaction data that we know. It's called cross-section. Cross-section because if you're looking at a football from far away, it looks like a circle. So imagine a nucleus is a football and you're striking it with a neutron. It's going to hit that, that football, that nucleon, that nucleus, and it looks like a circle. Now, if you visualize a bigger circle, then there's more chance of interaction. If you visualize a smaller circle, then there's a chance of missing it. So there's a small interaction cross-section. So a small cross-section indicates a small probability of a particular interaction. Now, nuclei are very small. So, and if you square that, you get something so small that you measure it in terms of these units, 10 to the minus 24 centimeters square. Now, the Manhattan Project days, late 30s and early 40s, gave this the code name of barn. So we call this unit a barn. 10 to the minus 24 centimeters square is a barn. And because there's so many interactions possible, a neutron hitting a nucleus can have a billiard ball collision. Let's call that an elastic scattering. It could lose energy by rubbing on the table, losing energy to friction. So let's call that inelastic scattering. It can be absorbed, meaning it can disappear in the nucleus which it collides with. It could have fission. In other words, it goes in, there's spallation of the compound nucleus which fragments, and then neutrons come out and energies come out, and that's called nuclear fission, such an important reaction that we're all interested in. Then radiative capture is possible, etc., etc. Radiative capture means that neutron gets captured and radiation comes out. So it's called an N-gamma reaction. N goes in, disappears, gamma comes out. So I'll call that an N-gamma reaction. And that's also called a radiative capture reaction, etc., etc. Now, etc. means that there are so many other possibilities. So if you want to see the sum of all of these, then let's call that the total cross-section, sigma t. Sigma is small, sigma because it's a microscopic cross-section. It's a natural data. It has nothing to do with how many atoms there are. It's just how a neutron behaves when it interacts with the nucleus. Now, in your context, of course, you don't have one neutron or one nucleus. You've got a certain number density, let's say it's capital N, of the host nuclei with which it's colliding. So we're going to see how we can calculate the number densities of graphite, uranium dioxide, uranium hexafluoride, boron carbide, whatever material that you make. For any application, you have to calculate the number density. Now, when you multiply that number density by the microscopic cross-section, you get the macroscopic cross-section, big sigma t, that's the definition. And since capital N is per cubic centimeter, the nuclei per cubic centimeter, and you multiply it by centimeter squared, so the units of this have got to be per centimeter, which means that you can think of it as the probability of, and well, a probability means it's got to be between 0 and 1. So if this number comes out to be 5, so if I get sigma t is 5 per centimeter, that means I'm going to have 5 interactions per centimeter of traveling of the neutron. Now, cross sections have been tabulated, experiments have been carried out, models have been made in great detail by national labs starting from the United States of America and into Europe, Japan, China. So lots and lots of experiments have been carried out. And so now we've got nuclear data libraries. Now, here let me show you just one of those so many cross sections just to introduce this concept to you. So this blue thing represents cross section, and it represents microscopic cross section, and so the units are barns. It's on the y-axis. You can see it's a log scale. On the x-axis, we've got the energy of the neutron, which is going to strike a nucleus. Now you can see that this is an MeV. So a fast neutron, an energetic neutron, is somewhere over here. A slow neutron, now remember it's slow by neutron standards, not by my and your standards. By our standards, it's still pretty fast. So we call these slow neutrons or thermal neutrons because they're thermalizing. So this is 10 to the minus 5 MeV, meaning it's 1 eV. So if this is 1 eV, that's 0.1 eV, 0.01 eV. So 0.02 eV is what we call thermal energy at 25 Celsius at about 300 K. So you can see that this region, it falls from about 200 barns down to about 10 barns. Here you've got lots and lots of peaks, and here we don't know what's happening. It's all mixed up. And here it comes down over here nicely. So there are three regions you see here. One, a nice fall, little change ups and downs here. But this area is what is called the resonance area. Here we've got resonant energies at which the nucleus vibrates. It's got its resonant frequencies. So for this, you've got to go into quantum mechanics, but this is the area where strange things can happen. So if you're, for example, right on the peak over here, so you've got a huge absorption of 10,000 barns, but if you're a little bit away from it, then you've got just 10 barns. So this is very sensitive to the energy of the neutron. Now, if you look at those three regions separately, this is the low energy region. It's a nice 1 over E behavior. If you look at the central region, the resonances, got a little bigger picture over here. Now these cross sections come out of the ENDF files, evaluated nuclear data files. You can tabulate them, they're available. I'll show you later on in this course. You can go to a site, there's so many sites you go to, you get the data, you plot it in a form that you can either see or you can use in digital form. So this is very important for us because this is how we design nuclear reactors and nuclear systems. So look at this range, 10 to the minus 5 to 10 to the minus 2 MeV. So this is where you've got resonances. Now let's look at the fast energy side of it. The fast energy is in MeV, million electron volts. Nice behavior over here, but this is the border between the resonances and the fast. So these are quite unresolved. Okay, so now you've got some idea what cross sections look like. So now let's come and see how can you calculate the number density. It's so important to get the interaction cross section, big sigma, for any interaction. Now, you know Avogadro's number, it says that there are 6.022 times 10 to the 23 atoms per gram atom for an element, or 6.022 times 10 to the 23 molecules per gram molecule for anything in nature. So that's what Avogadro's number is. And from there you can find, given its density and its molecular weight, you can find the number of atoms or the number of molecules. Now, let me show you that for water. We all know water, we drink water from a glass. Here's water. Now water has a density, let's say 1. Of course, water has a variable density. It can be, doesn't have to be 1, but let's assume that it's 1 at the conditions we are considering it. So density of water, if I take as 1 gram per cubic centimeter, Avogadro's number I take as 6.023 times 10 to the 23, and the molecular weight of water I take as 18. So I get this number, which is quite a big number. I get 10 to the 23 0.3346 times 10 to the 23 molecules per cubic centimeter. Now, if you are drinking a glass of water, so a glass of water, let's say if it's 1/4 of a liter, so it's 250 cubic centimeter. So multiply this by 2.5 times 10 to the 2. So you get a number like 10 to the 25. So you're drinking 10 to the 25 molecules of water when you have a glass of water. So that's a huge number. Now, from here, we can find the number of hydrogen and oxygen atoms because you know from the formula of water there is H2O. So each molecule of water has got 2 atoms of hydrogen on it. It's got 1 atom of oxygen on it. So the number of hydrogen atoms has got to be twice the number of water molecules. And the number of oxygen atoms has got to be equal to the number of water molecules. So that's how you can find, let's put in other numbers for, let's say for uranium-238, you can find a bigger number over here, 10 to the 24. Why do we write it as 10 to the 24? Because remember, we've got to multiply this by small sigma, and the units of that is in barns, so this is going to cancel out. Of course, you don't have to, but it's nice and neat. Okay, let's come to example 1.4. Let me show you from first principles because you know these are not the things that you get from books for every situation. So I've come across situations where I've had the need to calculate my own number densities for my own mixtures and combinations that I'm considering. And that could happen if you're doing an optimization of a radiation shield, for example, that what percentage of this and what percentage of that do you want to mix to give the best possible performance. So let's look at example 1.4. Remember, we're doing everything from an engineering perspective. So you're not just trying to learn it, to reproduce it. You're trying to learn it, to apply it, to design something. So that's why, as they all say, back to the board, back to first principles. So here, let's calculate the atomic fractions and atomic weight of an element given. So we're going to combine 2 elements and make it one mixture or a composite or whatever you'd like to think of it as. So let me take 2 elements. One is I, one is J. Each has an atomic weight. So one has AI and one has AJ. I told you the units, it's grams per gram atom. Because now we're talking about elements, not molecules. So we mix it. So this is up to us whether you put 60% of this or 30% of this. So let's say I take a weight fraction epsilon, which is the ith element, I mix it. And so the jth element has got to be 1 minus epsilon because these 2 numbers have got to add to 1. So the total weight is W, which is Wi plus Wj. Then for Ni and Nj atoms per cubic centimeter, since Avogadro's number is of any substance K weighs AK grams, we can write Ni and Nj. So if you divide Ni by Nj from these two, you get this, and you express them in terms of weight fractions, you get this, and you put in the epsilon, you get this. You rearrange the epsilons and you get this. So now we've got a relationship between the weight fraction and the individual things that we know. So now if you know how many n's you put of I and j, then you can calculate the weight fraction. Usually what happens is that I want to have a specific weight fraction and I do not know how many numbers there'll be because I can't see atoms with my eyes. So I am more interested in getting Ni over Nj. So Ni over Nj I can find from the atomic fraction. So Ni divided by Ni plus Nj over Nj divided by Ni plus Nj converts into atomic fractions for I and J. Let's write them as alpha I. So alpha I is actually Ni over Ni plus Nj. So if you write this ratio as the ratio of the atoms, then you rearrange this and you get atomic fractions in terms of weight fractions. Of course, alpha J is 1 minus alpha I. So here's a neat little relationship for atomic fractions, and here's the little neat relationship for weight fractions. How do they relate to each other? Let's see, because we don't want to mix things up. So let's see how they relate to each other. Okay. So if you put things together, this is how they relate to each other, that the atomic fraction over the weight fraction for any ith is given by the average atomic weight of the mixture divided by AI. And the atomic weight fraction of the mixture is given by the individual atomic weights multiplied by the weight fractions of each of these constituents. So simple. And remember, always go back to a two-component thing. If you have 4 or 5 constituent elements, no problem. You've got to understand the 1 and 2 component thing. Because if you know how to add 3 plus 2, then you know how to add 3000 and 2000 as well. So let's look at an application. Consider U235 and U238 mixed with weight fractions, 3% of U235 and 97% of U238. So this would be the typical nuclear fuel in a PWR, for example, 3%. When we say a pressurized water reactor has 3% enriched fuel, then this is what we mean, that the weight fraction of uranium-235 is 3%. Of course, it's got 234 and other isotopes, and I'm ignoring them over here because they're very small. But when you want to do a proper good calculation, then you've got to put in things the way they are. And I'm going to show you that later on. After about 10-15 lectures, we'll come to real reactor design. Right now, the concepts. Okay, so the average atomic weight of the mixture, A bar, is what I should first find out, and then apply the formulas that I just did above. So you can see that A bar from the weight fractions I get, so this is closer to 238 because naturally it's 97% 238. The atomic fractions from the above formula I calculated here for you, and we calculated the atomic fraction. Now see that the atomic fractions are not equal to the weight fractions. Okay, the weight fractions were 0.03 and 0.97. The atomic fractions are 0.0304 and 0.9696, so they're not the same. Now example 1.5, if you can read this, because it's flashing on the screen, so you can go through this yourself, calculate the density of a mixture prepared from 2 elements of given densities. Now sometimes people give you different data, they don't give you exactly what you want, so you've got to find things out of whatever data is available for you. Now that's why I gave you example 1.5, that I've asked you what is the density of this mixture. Now later on we're going to have quizzes and assignments and exams. So these are the kind of problems that you can expect, that I'll give you that 2 elements are combined in a 60-40% ratio. The individual densities are this and that, and tell me the density of the mixture. So again, back to first principles, you're going to write the volume fractions, then you're going to take X grams of the mixture, and you're going to get the density of the mixture in terms of the weight fractions and the density of the individual elements. You can extend that to an n component mixture. If I give you in the exam an n component mixture, then remember this little thing, which I've never been able to memorize. So I always do it slowly. I go back to the 2 component and then I generalize it to this. So here's an application, and let's now calculate the number density of each element in a molecular substance of whatever we are doing. So this is the formula that we derived above, and so we apply this to the data that is given over here. Now in this case, we have the weight fractions which are given. We've got 4% of uranium in uranium dioxide, which are typical fuel pellets. Now, assume that I've given you the density of uranium dioxide in reactor fuel, which is typically 10.9 grams per cubic centimeter. So again, from above, you first calculate the average atomic weight of uranium, from here. You find the atomic fractions as we did above. You find the molecular weight because you know now here you know the average atomic weight of uranium. Of course, oxygen is, you've got 2 atoms of oxygen in UO2. So let's say that it's 16, actually it's 15.9999, but let me take it as 16. So I get the average molecular weight of UO2 as 269.9269 grams per gram molecule. Now, I simply apply N equal to rho Avogadro over M. For UO2, I treat it as one thing. And again, I get numbers over here. Remember in engineering, when you get numbers, they're not just numbers that you blindly use. You look at them, the orders of magnitude looks good because whenever I have solids, I should have 10 to the 23 about. And whenever I have liquids, so 10 to the 21 about. And whenever I have gases, so 10 to the 19 about. So this looks all right. Now, as I said before, look at the formula UO2. A molecule of UO2 has one U and two O's. So the number density of U is the same as the number density of the molecules because each molecule has one U and each molecule has two O's, so that's going to be double that. So that is how we find the number densities of U and of U5 and U8. Okay, so that's how you prepare mixture cross sections. And remember, this is all part of pre-processing. So whenever you're making a data file of a nuclear simulation, then this is what you've got to do yourself. Okay, so I always take a lot of time doing these things because I want to get them right. Okay, now let's look at example 1.7 here. We determine the thermal macroscopic cross-section. What does the word thermal mean? I told you it means something that is in thermal equilibrium, E equal to KT, where K is Boltzmann's constant, T is the absolute temperature, thermal equilibrium. So in your room where you've got air, molecules are in equilibrium with each other. And that's why there's something called a temperature. You say the temperature today is 23 Celsius. So what does that mean? Actually, there's no such thing that there is a temperature because every molecule has got its own energy and its own temperature. So when you say there's a temperature, so you're assuming that things are in thermodynamic equilibrium. And that's exactly what we do for neutrons. We say that these are thermal neutrons, which means that they are neutrons in equilibrium with their surroundings. Surroundings can be carbon atoms, they can be steel, they can be anything that they're in. So when they are in equilibrium, that means they're giving and taking. They're not just giving or they're not just taking, they're giving and taking. So then that's called equilibrium, when things give and take and things stay kind of same. So that's called equilibrium. And you know that nature tries to achieve equilibrium in every, if there's a hot wall and a cold wall, then the hot one will try to get cold, the cold one will try to get hot until they come to an intermediate temperature. So here I want you to determine the thermal macroscopic cross-section, absorption cross-section, and the macroscopic fission cross-section for pure U235 using the data in this table. Compare these values with the fast reactor macroscopic. I'll come to what I mean by fast reactor. For the time being, you just assume that there are thermal reactors in the world and there are fast reactors. Fast reactor is something which has got neutrons which are moving fast, MEV. Now remember, the fastest neutron that we know travels 1/10 of the speed of light. So that's what we call a fast neutron. And what we call a thermal or a slow neutron is something that goes at 0.025 eV of energy. So these are some thermal cross sections of fissile nuclides, which I've taken from Lamarche and Barata, page 82. And you can see that the thermal absorption cross section in bars. Now here absorption means radiative capture plus fission. And alpha stands for fission divided by capture. So here you can see fission is fairly big, and here you can see fission is fairly small, capture is fairly big. And here it's about 0.2. So now we want a very high sigma A. So from here you can see that plutonium-239 is much better than uranium-235. Right? And so this is for a thermal cross-section. Now, if you look at fast cross-sections, so here's plutonium-239, and here's uranium-235. Here's plutonium-239, here's uranium-235. Compare fast with thermal, like I showed you that graph before. So thermal is 582 for U235, fast is just 1.65. So if you've got a fast reactor, this one, 1.4. So if you've got a fast reactor, see, you get such few fissions compared to if you have a thermal reactor. So that's why thermal reactors, so that's why you need to slow down neutrons so that you get better number of fissions. So let's calculate the thermal macroscopic absorption cross-section from the above. So I just want you to take these numbers from the tables and multiply it by the number density, and you get these things over here. Now, when you get numbers, again, what I would advise you as a professor, a number is not just a number. A number means something. So let's look at what does this mean. Now, sigma A, 33.147 per centimeter. So does that mean that when my neutron at thermal energy is going to travel 1 centimeter, it's going to undergo 33 absorptions? Yes, that's exactly what it means. So you've got to multiply this by the flux, integrate it over the volume to get the number of absorptions in any room or in any volume that you're interested in. So what I would say over here is that sigma A, if you take the inverse of sigma A, then what will be the units of per centimeter? They'll become centimeter. So the inverse of 1 of 33 is 1 over 33, which is 1 over 0.03. So I'll tell you that 0.03 centimeters in its travel, most probably there's going to be an absorption. Okay. So that's a good number and good engineering estimate, that 0.03 centimeters in its travel. For us, it's a tiny distance, isn't it? So 0.03 centimeters, there's going to be an absorption. Now, same thing for fission, same thing for fast absorption. Now, 1 over 0.08 is a much bigger number than 1 over 0.33. So if something is going fast, so it's going to have an absorption after it really travels a lot of distance, right? Maybe if this were 0.1, then it would be 10 centimeters. So after about 12 centimeters, you'd get an absorption for a fast neutron. But after about 0.03 centimeters, you would expect an absorption from a thermal neutron. So doesn't that tell you a lot about how you would design something from the engineering point of view? Now these are the inverses of those sigmas, and they're called mean free paths. Okay? So that's an important thing for you to know, mean free path. Now mean free path is the average, it's a measure of the average distance traveled between collisions for this particular reaction, in this case absorption, in this case fission, for thermal and for fast. Okay, so that's what I'm saying over here. Now you can go to example 1.8 and do the same thing yourself. Okay, now this is a picture which I've made myself, and it's such a nice picture, and it tells you so much. So in my mind, this is what I think fission is, and of course it was Lisa Meitner who first made this picture for uh, Otto Frisch. And when I was a student at Queen Mary College doing my BS, I had the opportunity to shake hands with Otto Frisch in London at a meeting of the Institution of Nuclear Engineers, where I went to with my professor when I was at Queen Mary College. And later on, I read that this is exactly the picture that Lisa might have said that here is a neutron striking, let's say U235, and it gets absorbed. So I made this little picture, and then it becomes wobbly. It becomes wobbly and it undergoes what is called spallation. It breaks up. So I put some yellow and red colors to show you some bright light, and all this happens in such a tiny amount of time that you'd think it's it's instantaneous. Fission happens much faster, but the process from here to here, from absorption to here, is this much, and look what comes out. So they get broken into two fragments, and two or sometimes three neutrons can come out. And you've got gamma radiation, and this is the beauty of it all, that you get energy. And this is how we produce electricity. And so again, about 200 MeV, 200 million electron volts comes out of this. It's a very small amount of energy. But when you multiply it by that n, which I showed you above, remember that's such a big number. So if you multiply this tiny energy by that big number, you get a big number. And when you get a big number, so you can use a lot of fuel with some enrichment. I told you U235 is much better than U238 from the sigma F cross sections. And you can produce 300 megawatt of electric power. You can run a little city. If you produce 1,000 megawatt of electric power, then we've got over 430 nuclear reactors in the world today, and they're all producing electricity. And I think it's about 1/6 of the world's electricity is produced by this reaction. So this was a great achievement for human beings. There are a number of books. Now, what comes out of fission? Well, it's not the same thing always. So it's stochastic, it's probable. But a typical nuclear reaction could be that a neutron strikes a uranium nucleus, and in one particular, you could get xenon and strontium. You could get two neutrons coming out, and you get a tiny little amount of energy. If you want to ask me that what comes out of fission, then I'll show you this graph that I don't know exactly what's going to come out, but I know that if you plot the fission yield in percentages versus mass number, then there's a 1% chance that these things are going to come out. And there's almost a 6-7% chance that these things are going to come out. But there's got to be conservation of mass. So if you look at this fission reaction that I showed you, so add up these numbers. So 1 plus 235 should give you 140 plus 94 is 234. And 234 plus 2 is 236, and that's exactly 235 plus 1. So there is conservation of material. Again, 92 is 54 plus 38 is 92. So that's called conservation of material. Okay, so over here, so that's what fissions are. There's a new bar which says the average number of neutrons coming out of fission. Now, these neutrons have a spectrum, which I'm going to show you. What do they look like? They're not all at the same energy. So one particular spectrum that I show you over here says that this is a typical fission spectrum. So distribution of energies. So you get few very high energy neutrons you could get coming out, but the probable energy, the most probable energy is somewhere here about less than 1 MeV. And I would say that a fission spectrum would give you about an average energy of, with this data, for uranium, it would give you about, the average energy would be close to 2 MeV. So there are various spectra that we use. We use the Watt spectrum, we use the Cranberg spectrum, Watt fission spectrum, which is similar to the Cranberg spectrum. So these models have been made, and you can see these models and how they are. So these are the empirical Maxwell and Cranberg spectrum. Okay. So here's the comparison for the energy that you would find the energy distribution. Okay, so now next lecture I'm going to begin with these examples where we're going to calculate the number of fissions in various sections of a reactor, and we'll see what we can do and how important those are. So, so I'll end this lecture over here.